Hello everyone, welcome to this online course on manufacturing processes. I am Kishore, Assistant Professor in the Department of Mechanical Engineering, MLR Institute of Technology, Hyderabad. So, in this manufacturing processes course, we have already covered or completed casting and welding, and we have started. One lecture is already completed on metal forming. So, in last class, we saw what is the meaning of metal forming, and then we saw how to classify the metal forming, that is in bulk deformation and then sheet metal forming. We also saw what are the processes there in bulk deformation, what are the processes there in sheet metal forming, and briefly we also saw what those processes are about. Okay, today we are starting with, in detail we will discuss now those processes. So we will start with the forging. So today we are starting with the forging. This is a bulk deformation process. So in today's lecture, we will start with forging. We'll see what is the meaning of forging. Okay. Then we'll also see how to classify the forging processes, on what basis this classification will be there. And then one of the forging operation we'll start with, that is open die forging. Okay. And then we'll try to take some numerical and solve based on this one. So today we'll start with this bulk deformation process, and we'll start with the forging. So what is the forging? We have already seen in forging, actually material will be deformed, but there will be die, and two die suppose are there. One that die is also known as platen. So force will be applied. Suppose one die is fixed, another will be there which can move, and workpiece will be inside. Will apply force and through that die. So because of that force, material will be deformed, and finally it will take the shape of the die, or whatever the impressions or whatever the cavity shape we have given. Actually, it will take. Now that force may be gradual, it may be sudden force. So accordingly, all these things has been classified. So one by one, we will see what is forging first. It is a deformation process. As we know, all these metal forming processes are nothing but deformation. That is plastic deformation. It's a deformation process, means the workpiece is compressed between the two dies. We have already seen through the diagram. Two dies means just like this one. This is the one die, and this is the another one. This you can see is fixed, and here our workpiece is. So it is compressed between the two die using either impact load, hydraulic load, or gradual load to deform. That totally depends the material that we are going to deform, and also what are the applications. Okay, so we can gradually deform the material, or through impact loading we can deform the material. Okay, now different energy sources, it may be hydraulic, it may be other the means of transferring the load. Okay, so depending upon the material we are going to follow this one. Okay, it is used to make a variety of high strength component. Okay, now so what happens through casting? Suppose we have produced a component, that was the primary manufacturing processes. To impart some other, it's increase strength or impart other property. These are the secondary processes which are generally being done on the component. So casting is generally this forging is generally being used on those kind of components to increase its strength, means increase the strength of the component, especially in those kind of application where, for example, if we are using a component in automotive, or you are using in aerospace or some other applications. So what happens? Primary processes are there through which we have manufactured the part. So increase its strength. Generally, forging is being conducted, or forging is done, or through forging material is being deformed in a particular shape. It will come to not only to change its shape or the dimension, but also to impart its extra property in the form of strength. Okay, the components include many things are there, like engine, crankshaft is there. Okay, then connecting rod is there, gears are there, aircraft structural components is there, jet engine, turbine parts are there. So many applications are there where forging is being used. But forging, as I said, is not a primary manufacturing process. Primary manufacturing process is like casting is there, powder metallurgy techniques are there. These are the secondary operations which are used to obviously change the shape and size. We can change, but not only that, we can impart the extra property, like in this one, high strength to the component, so that it will be applicable for this kind of special application. Okay. Now, how to classify this one? Depending upon many factors, it is being classified. At the starting, not starting, in the last lecture, we have already seen that it may be hot working, it may be cold working, depending upon at what temperature we are deforming the material. If you are deforming at room temperature, it will be cold. Okay. If you are deforming at temperature which is beyond the crystallization of the material, then it is hot working. But forging is generally a hot working process. Okay, means generally the material that we are going to forge will be forged at a temperature of more than the half of the melting of the material. Okay, now means it will be in the range of its recrystallization temperature. So that is the one of the criteria how it is being classified. What is the second criteria? That depend on the presses, that forces we are applying. So it may be impact loading, means if hammers we are using, through hammer we are applying the force to deform the material, or it may be through a gradual pressure application through presses. Okay, na, like compressive presses are there, means through presses we are gradually applying the load on the material that we are going to deform, or impact loading. So based on these two it is classified, either we are applying the sudden loading over there, or gradually we are applying the load. The third category is what is the shape, how, where we are deforming the material, means the die we are using, where we are deforming the material, whether it is open or it is closed. Depending upon that, it may be open die forging, where there will be no restriction in the flow of the material. We are applying the force, and in transverse direction material is free to flow. So it will be open die, impression die, or closed die forging, where there will be restriction on the material flow. Okay, now, or impression will be there, material will be fixed to flow in those area also only. And the last one is flashless forging. Actually, we'll see what is the meaning of this flashless. Okay, so first we are starting with the open die forging. Open die forging, as I told, in forging we have the die, and in between our workpiece is there. You can see here what I told. In open die there is no restriction, there is no restriction on the material flow. If I'm applying force from this one and this die is fixed, so what will happen? This cross-sectional area will increase of this material. Its cross-sectional area will increase and length will decrease. This height will decrease. So in this transverse direction, it is not, there is no any restriction that material flow will be restricted. It is free to flow. Okay, na. So this is known as open die. So in open die, workpiece is compressed between two flat platens. This die is also known as platens. Okay, na. This is at the top and this is at the bottom. Of course, it is fixed over there. Okay. So two flattened platens or die, thus allowing the metal to flow without any restriction in the sideward direction relative to the die surfaces. Yes, this is, as it is open, so there is no restriction in the material flow. It can, in transverse direction, it is free to flow, it is free to move. Simple example, what is the example of this one? Compression of a billet between two flat dies half, which is like compression test. Yeah, in diagram it is clear. So just like compression test, we have to suppose increase the cross section area. I told when we started this one, if I have to increase the cross section area, so from both sides I'm applying the force. What is happening? Cross section area will increase, and what will happen? Its length will decrease. So this is the best example we can understand the open die forging. Means in cross sectional, means in sideward direction, there is no restriction over there on the material flow. Okay, this is also known as upsetting. Upsetting means increasing the cross sectional area and decreasing the length. Okay, basically height decreases, yeah, and diameter increase. This is also known as upsetting. Upsetting, this is also known as upsetting. Okay, under ideal conditions, what is the meaning of ideal condition? And ideal condition means wherever this platen or die is in contact with the workpiece, there is no friction. Here there is no friction, here also there is no friction. This is known as ideal condition. So whenever there is ideal condition, there is no bulging of the material. What is the bulging? Means it will not take this kind of shape. Okay, now why? Because here it is not fixed, it is not fixed. As I am applying the pressure, this pressure is distributed uniformly. So material will deform uniformly. Its length uniformly, homogeneously, it will deform, and its length will decrease uniformly, and area of cross sectional will increase uniformly. But if friction is there in this area, then there will be problem. Then the material flow in these sections and material flow in this section, it's not going to be same. Okay, so because of that, what will happen? Material will bulge out from the middle. That is given here. Where there is no friction between the billet and die surfaces, this is known as ideal condition. Homogeneous deformation occurs. Yes, throughout there will be homogeneous deformation. In this case, diameter increases uniformly throughout its height. Yes. So if like this we are deforming, and this is the material, okay now. So this cross sectional will increase uniformly throughout the height. Means whatever the increase is at this, everywhere it is going to be same. So it will be uniform. But if friction is there in this area, here there is friction. So deformation, for example, in this part, deformation in this part, and here it is not going to be same. It is going to be a problem. So what will happen? Because of that, it will start bulging from the center. It will start bulging. So there will be bulging over there. So in ideal condition, yes, strain we can write simply is equal to ln initial height upon final height. Okay, h is equal to hf at the end of the compression. Okay, and a force F, simply flow stress sigma F, we can write force upon area. There will be no problem in this one. Okay, but if it is not an ideal condition, then what will happen? You can see here in ideal condition, this is the ideal condition. Ideal ideal condition means there is no friction here, there is no friction here, there is no friction. So what is happening? You can see here throughout the height, this throughout the height, the increase in cross sectional area is uniform. So you can see here, but this is not the case here. This is actually not an ideal case. Means there is friction here, there is friction here, there is friction. Wherever the workpiece is in contact with the die, there is friction over there, and because of the friction, deformation is not homogeneous. And it is not homogeneous means throughout the height, whatever the increase is there in the cross sectional area, it is not uniform. So what will happen? There will be bulging. So you can see here, there is bulging. Okay, no, there is bulging in the work. So it is not uniform. Why it is happening? Because of the friction. So this is not a ideal condition. The same thing has been written here. In actual forging operation, in actual, definitely if actual is there, friction definitely will be there. Depending, it may be less, it may be more, but definitely friction will be there. Deformation will not be homogeneous as bulging occurs because of the presence of friction at the die billet interface. This friction opposes the movement of billet at the surface. This is known as barreling effect. This is actually a defect in forging. This is known as barreling effect. Okay. So what is this barreling effect? Because of the friction at the interface. Interface means where the workpiece is in contact with the die. When you are applying the force, the increase in cross sectional area or the deformation is not going to be homogeneous. So what will happen at the center? There will be bulging. This is known as barreling effect. Okay, the barreling effect will significant at the diameter to height ratio of the work part increases. As this d by h ratio is increased, it is going to be more effective. Okay, due to the greater contact area at the billet die interface. Temperature also affect the barreling effect. Obviously, it will affect because temperature will affect the friction, and if friction is affected, so obviously this barreling effect will also be dependent upon the temperature. So now this equation will change. Now this force F is not going to be sigma F into A. Now it will be Kf into A. This is a factor depends on many parameter. Okay. So whenever there will be friction or the actual forging will be there, obviously these problems are going to be there. Okay. Now we'll take this numerical. It's a simple numerical just to understand. It's easy that strain formula we saw now how to this strain was. So based on that we are going to do this numerical. Okay. So what this numerical is, calculate the true strain for a low carbon steel bar which is doubled in length by forging of this. Okay. So we have a bar, suppose This is the die, this is the upper die, and this is the lower die. Okay, now so no diagram. This diagram is not that one. We have to increase the length. Here it is doubled. The length is increased. So if you are applying this, cross sectional area will decrease. So what we have to do? This diagram will be different. What will be the diagram? So let me remove this one. Yeah, diagram will look like this. Suppose this is my workpiece. Okay, now this is my workpiece, and here the die was platen. Okay, yes. Here the die or the platen is. This is the die half. This is also the die half. Okay. So if we'll apply force from here and from here, for example, so what will happen? This bar will increase in length. So suppose initially it is L naught. So finally it will become, obviously its cross sectional area will reduce and it will become 2L naught. Okay. That's what has been given in the problem. What is given? Calculate the true strain. That is true strain for a low carbon steel bar which is doubled in length by forging operation. So if two platens are there, two dies are there, our workpiece is over there, we are applying the force, and because of the forging operation, what is happening? Length is becoming double, means it is increasing. So initially if it is L naught, it has become twice L naught. And what we have to calculate, it has been asked to calculate the true strain. So there is formula for true strain. What is the formula for true strain? So what are the given things in this one? It is given initial length is equal to L naught, and final length is equal to twice L naught. It is given, it has been increased by, so we have to calculate true strain. This is equal to what? This is the question. So we know the formula. True strain is equal to, what is the formula? The formula for this one is, true strain formula is final length LF upon LI. Now this is ln, natural logarithm. So what is this? Ln. What is the final length? Twice L naught. And what is the initial length? L naught. L naught and L naught will be cancelled out. So this will become ln2. Natural logarithm of 2. What is the value of natural logarithm of 2? So natural logarithm of 2, the value comes out. This value is, what is the value of natural logarithm of this one? It is 0.693. And this is 0.693. That will be the answer. It's a very simple question. What we have to remember, that this formula, this true strain, that is true strain, this formula need to understand or remember. True strain, it is generally denoted by silent t. This is equal to ln natural logarithm final length upon initial length. That we need to keep in mind. If it is a progressive deformation, means it is deformed, again deformed, again deformed, there will be no problem. What you have to keep in mind, what is the final length? Although there is progressive deformation in the material, what is the final length and what is the initial length? What was the initial length? You just have to take the ratio and logarithm, natural logarithm of that one. That will give you true strain value. Okay. So we'll stop this lecture here, and next lecture we'll come up with some other metal forming process. Thank you.